then just where the two come together like that.
Close it.
I think close it. There. Okay.
Now, can I see your slides? This is a good question. I told you I had the surgery, so I'm still,
Yeah.
I don't know if I might have to. Hey, Ryan.
Here we go. Doesn't help.
Okay. What did happen? No, that's coordination. All right. Hello? Yes. I was just about to, and I sent you an email and forgot to add Courtney's name to it. She says that she can, she's out of town and isn't coming back till tomorrow, but she said it could be set up, you know, for 3 o'clock if that works for you. Okay. To come back over to my building, yeah. I will write her back again and see if that works. Why don't you get me the slides from your talk? You don't have to edit it because it'll be good enough for me to do the questions for you from that.
Hello, the attendees online. Can anyone hear me?
No. I can provide it. I was going to provide it, but I could provide it.
Thank you. And I'm hoping that you all can see the screen.
PowerPoint if you didn't.
Yes.
Wonderful.
Probably,
Thank you.
But it wasn't the animations. It was like if you had a visual that there's no other explanation and that you were going to be talking about, you may want to put some notes in or something. You know, but that we don't have to do that now.
Yeah, we're going to get started in a couple of minutes.
You just got me your slides. I can make up some questions that basically it'll be you're providing a good overview of the slides, and then they can have them to look at in depth later. But we can work on them later. So, yeah, just send them on to me the way you had them, and I'll come up with questions for you. I will do that. Okay, thanks. Bye.
I think it's time.
Okay, we've got people online. All right. Okay. Let me turn off the sound on this. and I'll sit closer to the front so I can see. And they can they hear us okay?
Yes. Just check. We can hear us.
Okay. Those of you who are on GoToMeeting, that's good because you're nice and dry. The weather here is not so great and not too many people are here, so we're actually going to be talking entirely to you all. Welcome to the second session. This is a new one in our series, and Dr. Ben Ozaydin from the Department of Health Services Administration and the Health Informatics programs is going to be giving the talk. Again, afterwards, I will be sending out the materials from this talk. So without further ado, we'll let Dr. Ozaydin start.
Thank you very much, Dr. Berner. All right. Hello, everyone. Good afternoon. Thank you all for coming in, and hopefully it will be a nice, informative session today. Our title today is Watson, Clinical Data Mining and You. By Watson, we want to get your attention for artificial intelligence and machine learning, actually, data mining using machine learning. And by you, we are referring to how clinicians and people in the discipline of medicine can utilize these tools. What are these tools good for? What are they not good for? So let's get started. A little bit background on me. My name is Ben Ozaydin. I have been at UAB for a long time, since I graduated from college, actually. My bachelor's was in physics, and then I got my master's in electrical engineering and my PhD in computer engineering. My dissertation was on systems analysis and modeling. During my PhD studies, I started working in the Department of Ophthalmology, initially working with clinical research databases, creating, managing them, and then working on projects involving image processing, classification, pattern recognition, predictive analytics, the kinds of topics that are relevant to us today. And then I've also later worked at the Department of Anesthesiology, and there I did system administration, database administration. I worked with UAB's Enterprise Data Warehouse on the health system side, and we also developed the anesthesiology dashboard for our physicians and actually for the entire staff of anesthesiology for compliance purposes, for our schedules, dynamic OR scheduling, etc. It was a comprehensive system, dashboard system. And currently I'm with the Health Informatics graduate programs at Health Services Administration Department, and some of the areas of my research interests are decision support systems, and some of the projects that we are working currently are decision support systems with predictive analytics to optimize long-term care staffing. This is for skilled nursing homes. And we are also working on a data warehouse project. It's a combination of data warehouse and data analytics tool that we're working on for Health Services Administration related databases. We are also started working on, we're searching funding for integrated multi-disease chronic care management system for real-time monitoring and clinical decision support. And lately I've been working on a text mining analysis of mHealth research, and also that's another interest of mine to do text mining portion of machine learning. I forgot to say, but anytime during the presentation, please feel free to interrupt, and if you have any questions or comments, otherwise I'll continue. So some of the things that we're going to touch on today, we're talking about clinical data mining as an umbrella concept. As we go through, I'm going to want to give some background information before we could attempt using machine learning anywhere in healthcare domain. There are some systems that needs to be in place, and we're going to talk about those more fundamental systems. And as a broad view, we're going to talk about healthcare data in general, the systems that are around this data, and then go into data mining and analytics, and what it is, what kind of methods and tools are used in there, and the status of data analytics in healthcare domain. And then from there, we're going to talk about machine learning, and that's what Watson in the title refers to, which we're going to look at machine learning as a mechanism to learn from data. And we're going to look at some applications of machine learning on clinical data, and we will look also at how we would use it, what it is good for. This is the U part of the title. What are the appropriate uses? What are some of the uses that people have misconceptions, and this kind of techniques are not appropriate for? And we're going to also talk about what kind of conclusions can be drawn using these techniques, and which ones would not be appropriate. Just to start with, when Dr. Bernard talked to me about this topic being one of the topics in the seminar series this year, and around the same time, the latest issue of JAMIA, this is Journal of American Medical Informatics Association, it came out, and when I look at the highlighted papers on the cover, they had 5 highlighted papers, and a couple of them were about predictive analytics. One was predicting order patterns using probabilistic topic models. Another one was using knowledge-driven genomic interactions for multi-omics data analysis. It's a multidimensional model for predicting clinical outcomes in cancer research. And a third one actually was about text mining, natural language processing type of paper. It was using social media to monitor mental health discussions on Twitter. So 3 out of 5 papers that are on the cover were related to our topic today. This is the main journal for health informatics. That tells me that this topic is really a hot topic in this day and age in healthcare, and I think it's a very appropriate topic for the seminar as well. And going further, looking at the table of contents, here we have out of 17 papers, excluding the reviews, 7 of them were about some kind of machine learning. We had, like I said, predictive topic modeling. They had machine learning web classifier. They had neural networks using grammatical evolution type of neural networks. Autoregressive prediction model was one of them. We talked about the text mining on social media. One was using recurrent neural networks, and of course the natural language processing. So this is really an appropriate time to actually visit these topics, and a lot of people are utilizing machine learning algorithms to approach the problems in healthcare. And the other reason for it to be available now, machine learning has been around for a long time, but with the improvements in both hardware and software algorithms, now it's easier than ever to be able to actually perform these tasks, whereas early on, all the algorithms were still out there, but the computer hardware was not there for us to be able to actually effectively perform machine learning techniques. So as I said, we take a step back, and before we would be able to talk about machine learning, what kind of fundamental systems should exist? And as we get to that, I want to talk a little bit about the journey of health data, where the data gets generated initially, what kind of systems aggregated, what kind of systems analyze and get knowledge out of health data, and what kind of systems exist for reporting and visualization purposes. First, the data that gets generated for healthcare, initially what comes to mind is the clinical data. Of course, the clinical record is part of health data, but that's only one category of health data. We have administration data, clinical research data, individualized data that could be categorized under precision medicine, and lately more and more of patient-generated data, population-level data, all the way from clinical record up to patient-generated. We're talking about data where the unit of analysis is the patient, but we also have population-level data with population health, especially being an important topic lately, and also provider-level data. As part of the clinical record, electronic health record is one part of it. On top of that, there are also there's this electronic health record system, but there are also other systems, sometimes still collecting parts of the clinical record, may or may not be part of the EHR system. So those could be the labs data. Lately, more and more of these categories of data is part of the EHR system, but you will still see hospitals where there's an EHR system and there are additional systems that are taking care of different portions of the clinical record. On the administration side, of course, we have admittance, discharge, billing, claim data, different types of scheduling data for inpatient, outpatient, or we have utilization type of data. On top of that, we also have administrative data that are not specific to the healthcare domain, like HR, payroll, and financial administrative data that exist in any industry. So going on with the data generating systems, the third category is of course, we have data that are coming from clinical trials, from clinical research studies, from registries. We have data that are related to precision medicine, genomics data, phenomics data, microbiome data that we are encountering more and more. And on top of that, very large amounts of patient-generated data with Internet of Things type of devices that are used at our homes. This is the sensor data that gets generated from many, many different types of devices with variables, Internet of Things, and also on top of that, the data that gets generated on social media and patient portals and so on. And last but not least, we have population level data. We have data that's collected by national or regional surveys or indices. We have epidemiological data, and also provider level data where health service research is more interested in, with the quality scores of the providers, hospitals, satisfaction scores, inspection data, and different services that the hospitals provide. So let's go back to this categories of systems that are around these type of health data. We talked about the data generating system, and these systems get accumulated on data warehouse type of systems, and then move into data analytics, knowledge extraction type of systems, and then of course reporting and visualization. Another perspective of looking at this health data system categories, we would look at data generating systems, as we talked about, in 5 different categories. And on the data warehouse type of systems, we usually have enterprise data warehouses that are institution specific. So different systems that are generating data, different categories of systems that are generating data get accumulated in a single data warehouse per that institution. And on top of these data warehouse systems, we are able to build data analytics and business intelligence systems. You see, we have to have all these fundamental parts before we even start talking about any kind of robust data analytics kinds of systems or business intelligence types of systems in healthcare. And of course, on top of these analytics and business intelligence systems, we have visualization and reporting systems. Well, we also said that we don't only have patient-level data, which gets generated in these 5 categories of system. We also have population and provider-level data that gets generated in other types of system, like survey data and etc. And then those type of data also get accumulated other data warehouse systems that are separate from institution-specific data warehouse systems because they are, by definition, not per institution, but accumulation of institutions. So when we look at this picture of fundamental systems that are around healthcare data, where do some of the other things like decision support systems, health information exchange type of systems fit? Well, the institution-specific enterprise data warehouses feed data into systems of data warehouse networks. For example, at our institution, it's going to be one of the topics in upcoming talks, we have our enterprise data warehouse and a system called I2B2 that's built on top of it, where the identified data can be used by anyone who has Blazor ID and requests to access it. And then that I2B2 data is also connected to what we call a shrine network, which is I2B2 systems of multiple institutions. So sorry, is there a question? Okay. So there exist these kind of systems that accumulate data from institution-specific data warehouse systems. You also have decision support systems, and there are 2 kinds of decision support systems. The types of decision support systems that require real-time data directly coming from EHR or ADT or other systems of an institution. And there are also decision support systems that do not require real-time data, and they would be okay using retrospective data. So the ones that require real-time data would actually fit right on top of the operational systems, the data generating systems, so that they can immediately access a lab result, for example, as soon as it's in the system, if a decision support is using that piece of data. But the decision support systems that do not require real-time data, they're depending on retrospective data, it's okay for them to sit on top of the data analytics, business intelligence type of systems, because data will get from data generating systems into the data warehouse. That's going to probably take some time. I think at UAB it's about 24 hours. Every night there's a data dump. And then data analytics and business intelligence systems are going to work on that data, and then you could have decision support systems that are based on that data. And these type of systems would be generating reports for, quarterly, weekly reports for the institution, for the administration. And also we have the systems that are used for interoperability and health information exchange type of systems. And these systems get their data also from the enterprise data warehouse because it's not necessarily have to be a real-time type of systems. So there are lots of organizations that have gone through and created these systems for themselves or got together and created their data warehouse networks or got involved with interoperability. But the next challenge now is that, once we have all these, and if these systems are really separate from each other, then we don't have anything coming back to these data generating systems. So the next challenge for healthcare is, and there are organizations that are already attacking this, to be able to get feedback after you have all your analysis, after you have all your business intelligence, knowledge extraction from your data. Now, being able to get those results back into the data generating system, which could be your electronic health record with some kind of decision support system, or it could be your some of your research databases. Whatever knowledge that gets extracted at the end of the day from these higher tier level systems, it's a challenge to actually have a feedback back into the data generating systems. And as a transition for us to go into machine learning, now HIMSS is Health Informatics Society. They came up with a maturity model for electronic medical record adoption. And they came up with a 7-stage maturity model. And it was very effective as hospitals were adopting electronic medical records. They would fill out surveys for HIMSS, and HIMSS would determine what stage of adoption model the hospitals are. And there were incentives for the hospitals to move on to higher stages. So currently, this is as of the fourth quarter of 2016. As you see, many of the hospitals are in stages 5 and 6. That's the majority, about 65%. But on level 7, on stage 7, which is the complete EMR adoption, complete adoption of the electronic medical record, plus data analytics to improve care. That's stage 7. So we have close to 5% of hospitals that are at that stage. So it is difficult. And as I talked about from the early of the presentation up to now, it requires all those fundamental systems in place before you can actually do meaningful, robust data analytics. So I think last year or year and a half ago, HIMSS came up with another adoption model. This time, it's not adoption of just electronic medical record, but adoption model for analytics maturity. So that stage 7, which was for data analytics, for use of data analytics for clinical care, has been expanded into its own 7 stages. Now they are looking at maturity model for analytics maturity, and again, this is also an incentive for the health systems to move up on these stages and get. It's a matter of also marketing for for health institutions as well. At the top of this, we see two things. One is predictive analytics at stage 6, and at stage 7, prescriptive analytics. So we are coming back to the main topic of this presentation, and we're going to talk about machine learning from the perspective of predictive analytics and prescriptive analytics. So in the literature, generally, the phases of analytics are described as descriptive. With descriptive analytics, we're looking at summaries of data and charts and reports. And it usually mostly just statistical analysis. And even within statistical analysis, it's mostly just descriptive analysis. The kinds of things like how many cases have been done in a given period of time for a given department or an institution as a whole, or average number of cases per clinician or per department, those kind of descriptive summaries of reports. But moving into predictive and prescriptive analysis, statistical analysis alone is not enough. Most of these type of analytics will require some level of machine learning. And when I use the term machine learning, I'm also, in this context, it's synonym to artificial intelligence type of techniques. So with predictive analytics, we are talking about analyses of past data to be able to identify patterns or relationships. And once those are identified, extrapolating those kind of analyses to forecast what's going to happen in the future. So there's a misconception of predictive analytics telling us what's going to happen in the future. That's not the case. Predictive analytics is telling us, based on past data, what might the future data look like, not necessarily what is going to happen in the future. Okay, so that's the subtle difference. So we don't necessarily predict the future, we forecast what might be happening in the future based on what data we have. And on prescriptive analytics, we're talking about the types of analyses to identify the best alternatives to optimize objects of interest. We might be wanting to increase our revenue. We might be wanting to increase patient satisfaction. Those could be our interests. So whatever our interest is, prescriptive analytics will tell us, utilizing the results of predictive analytics and comparing results of those predictive analytics, what would be the best way to actually achieve whatever goal we set out to do. Since prescriptive analytics requires use of predictive, also both of these analytics techniques require some use of machine learning techniques. Okay, so after this background information, let's get to actually what we mean by data mining using machine learning techniques. Data mining using machine learning techniques is a process of discovery of the patterns or relationships that exist in the raw data. And statistical analysis does that to an extent, but with machine learning, we are taking it to a next level in terms of number of data parameters that we can include in our analytics. So the main task that it performs is to extract patterns and relationships that exist in the raw data. It primarily deals with three types of problems, either problems of classification, problems of prediction, or problems of pattern recognition. And as a discipline, it sits in the intersection of statistics in math and computer science. Statistics brings us the methods and tools that we use to find the relationships among data. And from computer science, well, statistics had this all anyway, and we had been using statistical analysis for a long time for this same purpose, but then it had limitations in terms of number of observations we could include, in terms of number of data parameters that we could include, number of predictors we could include, number of classifiers we could include. So when we want to go beyond those limitations, now the techniques that are used in computer science, which are efficient algorithms that are more appropriate for larger data sets to be able to process them, that's where the contribution of computer science comes into machine learning. So the systems that we talked about, mainly the clinical decision support type of systems, those would be the types of systems that would utilize this information, right? Because why are we searching patterns in the data? That could be for research purposes, but even what's research, that is so that it will inform us for future decisions, whether those are policy type of decisions or other type of decisions. At the end of the day, it can be categorized under a decision support system. So most of the traditional decision support systems, especially in the field of medicine, are based on expert systems. And by that, what we mean are there are computer systems created that utilize guidelines and a preset set of rules in their rules engine. And when there's an incoming data, there are algorithms that utilize these guidelines, and they come up with a decision based on what the guideline says. On the other hand, with machine learning uses the raw data, not determined guidelines or the predetermined set of rules. Instead of being driven by a preset set of rules, machine learning is driven by learning from the data. So asking questions to the data, or we're going to look at two different types of machine learning, supervised versus unsupervised. In one, asking questions to the data, how to classify it, versus on the other, not even asking any questions, just asking machine learning to go find patterns, whatever it can find, given all that raw data. So on the reference that I was given by Dr. Berner, when I started looking at this, the authors were talking about making a comparison like expert systems. You can think about them like medical students who are applying whatever general principles they learn in medical school to each case for their patients, versus like residents who already have understanding of these guidelines, and as they go through from case to case, they are discovering rules and guidelines, and they are coming up with, they are increasing their expertise in that field. So medical students are applying whatever guidelines given to them, versus residents are actually learning from the data, learning from the cases that they experience. So we can compare expert systems versus systems that utilize machine learning, medical students who are just applying the rules to the cases versus residents who are actually learning from their cases. So we talked about some of the things that machine learning does already being done by statistical analysis, which main portion of it is the regression models, linear regression in statistical analysis, right? That we use that for classification. To an extent, an extension of classification, we use that for pattern recognition as well. Both regression models and machine learning models, they are using statistical functions to link independent variables to outcome variables, right? So we have independent variable outcome, and then some kind of a statistical function in between that models whatever behavior we're researching. Machine learning does the same, but as I referred to it a little bit ago, it can also handle much larger number of predictors, a larger number of independent variables. And on some problems, number of independent variables are larger than number of observations we have. Now, let's think about an Excel spreadsheet that has some research data on it. You would usually have more number of rows, which are your observations, your subjects, than your number of columns, which are your variables. But in some cases, you have more columns than rows. For example, let's think about image processing. Let's say we're processing images. Every single pixel of the image is a data point. It's a variable. So most of the time, you have, let's say you have a high resolution image, 3000 by 5000, you have 15 million data points. You don't necessarily have 15 million clinical trial subjects. So at some point, your number of predictors go so high where it surpasses your number of observations. So machine learning can handle that, regression models can. Machine learning also allows nonlinear approaches and interactive approaches. With linear regression, you don't necessarily interact with how the model is coming up with the result, how it's forming that statistical function that's between the independent variables and the outcomes. And another difference is that instead of coding the data for regression models, machine learning can handle all data. Okay. So for example, again, if you're going to talk about, again, imaging, let's say we have patient x-rays, and radiologists would take them and then give us a coded response in terms of what that x-ray shows. And in our regression models for our clinical studies, we would use that coded information. But with machine learning, instead of having someone summarize the data for you, you can actually process the entire data. Okay, so we kind of transitioned into, okay, what were the traditional systems and what are the benefits of the machine learning type of systems. Now let's talk about a little bit of categories of machine learning systems. There are mainly two categories of methods that are used for machine learning. One is called supervised learning, the other is called unsupervised learning. With supervised learning, we are dealing with predetermined categories or outcomes. Remember, we are dealing with classification problem, prediction problem, and pattern recognition problem. So I can, before we start applying any methods, we can talk about what the expected outcomes are going to be, and then tell that to our model, and then start from that point. Or we can tell our model, well, we don't know what the expected outcomes are, or we don't want to assume what the expected outcomes are. We are just going to let the model figure it out. Let the model put the categories in place, do the clustering, do the classification, and then we will look at those classes, those categories, and then figure out semantically what they mean. So if you provide the predetermined categories or outcomes into the system, we call those kind of methods of machine learning the supervised learning. If you don't, then we call them unsupervised learning. The supervised learning types of methods are usually used for the kinds of tasks that are done for classification or prediction, whereas for unsupervised, we don't really know what classes we're looking at. Again, at the end of the day, we can use unsupervised learning for classification as well, but it's going to be classification of unknown categories. So mainly the unsupervised learning techniques are used for pattern recognition that might exist in the raw data. With the supervised learning, the kind of tasks that we're doing, those are the kinds of tasks that are already being done by the experts of that domain, in our case, the physicians. Or with the unsupervised learning, we don't even know what we're going to figure out. So the kinds of tasks that we look at are not usually something that the domain experts are aware of. And lastly, on the supervised learning, you may find some relationships that are not obvious. That's usually not the case because we predetermine what the classification outcomes are going to be. But sometimes, on top of what we determined, predetermined, there's another category that we did not think about. So it could be non-obvious for a human being, a category, additional category that's not obvious for a human being, but the results of the supervised learning techniques may give us that category. Or we may think about two categories as distinct categories, but the results of supervised learning may prove us wrong, making those categories closer together. Versus on unsupervised version, the method is going to provide us with a number of categories which are not determined. So the experts need to look at what falls under those categories and see whether or not those categories make sense. If they do, name those categories and see what they actually mean. Lately, there are also techniques that combine both methods, supervised and unsupervised. Unsupervised first. So unsupervised techniques would be applied to raw data to come up with some categories of data. And then supervised techniques would be fed those categories. And then they use it together. It's called deep learning, which Watson is based on. When it was playing Jeopardy, I think that was the first time they used deep learning, the combination of unsupervised learning and supervised learning together. And it was proven to be very, very effective. Okay, are there any questions so far?
Could you give an example, like, I don't know, symptoms of a heart attack or something like that for each of those?
For supervised versus unsupervised?
Yeah,
okay.
like a clinical example.
Yeah, so one thing that I was working on when I was working in ophthalmology was I was working on glaucoma data. And there were predetermined outcomes. We had patients that had glaucoma. We had patients that we called normals, that did not have glaucoma. So when we were doing machine learning and we were applying machine learning techniques, we had two choices. We would either, when we are training our machine, then we would give those predetermined categories, the binary category, glaucomatous versus normal, and then train our supervised neural network technique that way. Versus we would say, yes, there is glaucomatous versus none, but there are also degrees of severity in terms of the patients that have glaucoma. So why, say that this is binary outcome, let's not give it anything and then see what kind of patterns we see from the data. So that kind of application of machine learning would be unsupervised versus the first one that I talked about, where we actually feed the two expected outcomes into the machine, glaucomatous versus normal. That would be supervised.
And when you did that, you were looking for features that predicted those? I mean,
absolutely. And actually, you're looking at two things that are machine learning techniques that are black box type of techniques. And at the end of the day, you get a statistical function that connects the input variables to the output variables, but you don't necessarily know what goes on inside black box type of techniques. So next time you feed in similar data, it gives you a result, but you don't know how it got calculated. There are also other techniques that are not black box. So if those are the techniques that you use, then you would be able to say, okay, these are the features that are affecting the outcome. So with logistic regression, for example, you would be able to say which independent variable is having what percentage of effect on the dependent variable. Versus neural network type of supervised machine learning, it's a black box type of thing. You would not be able to figure that out. But the goal is twofold. One is, the main goal is to have a machine that would predict the outcome accurately. That's the main goal. And as a side goal, sometimes you want to be able to say which features of my incoming data affected the outcome. So some of the methods that are used in supervised machine learning methods, one is the very common one is decision trees, like random forest. Decision trees map the features to an outcome. So for machine learning methods to work, the way it's performed is that the data that exists is separated into two. The first part is called the training data, and the second part, test data or verification data. So you would use the training data to train the machine for the statistical function that you're looking for between your inputs and outputs. And then your verification data would be used. In your verification data, you already know the outcomes. I'm talking about supervised because we have known outcomes here. And then you would use that to see if your machine is performing well. The common problem is that you may have your machine overfitting for your training data, and it would be great only for your training data, but other incoming data, it may not perform as well. That's why we do this with the verification. And if the result, if it doesn't perform well, then we go and retrain it with a different model. So that's decision trees are one. Logistic regression, of course, is a very common method. And neural networks are also a method where they predict outcome based on transformed representations of the features. So you take a set of features as your independent variables, and the neural network transforms them. It keeps transforming them however many layers you have, and then they eventually transform into your outcome. But you don't know what goes on in between inputs and outputs. That's why it's called a black box type of method. An improvement to neural network methods came about with support vector machines, and they are able to tackle the problem of generalizing the training data, the overfitting issue. And it became, support vector machines increased the performance of neural networks very much, and they became the most popular, best performing technique usually. Another technique is nearest neighbor algorithm, which assigns class based on values of the most similar training examples. So in your training data, it looks at which data values are similar together, and then it makes them neighbor and creates a class for them. On the unsupervised side, we have cluster analysis. That's mainly it. We don't have much different techniques, but we have techniques that are used under cluster analysis. Most famous one, latent class analysis, and in text mining usually there is latent semantic analysis. And then again neural networks, but artificial neural networks because they don't know the outcome variables. Some of the methods that are related to cluster analysis you would use remember with the unsupervised, you're giving all raw data without any indication what the outcomes could be. So if we want to save some processing time and do our, if we want our model to perform fast, then we would go through some dimension reductions so that we're not dealing with huge number of cases. And then single value decomposition would be used for that. And there's also a technique of principal component analysis that is used for cluster analysis. There are other techniques that are used for as part of machine learning models. Those are algorithms that are inspired by natural systems like genetic systems, biological systems, quantum systems, fuzzy logic type of systems. And also there are also algorithms that use a hybrid algorithm that pieces and bits and pieces are from each of these. Those are more sophisticated techniques. Okay, we talked about the benefits. We talked about the improvements from traditional models, statistical models. But what are the problems? What are the challenges with the machine learning techniques? Well, one thing is that what goes on in the black box, especially the neural network type of models, is not magic. It's math. And it needs interpretation. Math is not specific to one domain or another. It doesn't know what the domain is, whether you're doing these techniques in finance or medicine. You know, it doesn't know anything about that. It's just pure math. So domain experts and data scientists have to collaborate at every step to give meaning to what they find out. These are very iterative processes, machine learning processes. So these models are not single step, they're sophisticated multi-step processes. So at the end of each step, results have to be analyzed both by the data scientists and the domain experts, physicians in healthcare, to give meaning to what those results are. If they don't make sense, it's an iterative process, go back, find out what went wrong, modify the model, apply again, etc. Another problem is it's a pitfall. It's the causal inference. You know, predictors may not always be the cause of the outcome. With these models, what we are able to demonstrate is some kind of a correlation, not necessarily a causation. Now, this feature is correlated with this feature, but it may not cause it. So again, going back to the first problem, constant communication with the domain expert and data scientist to actually give meaning to to what's going on at every stage is critical. That's why, although we see a lot of projects that are coming out in this space, we don't see as much because it's really difficult. It requires efforts from many disciplines. Of course, main issue with any kind of data analytics, the quality of the incoming data. Garbage in, garbage out. It doesn't matter how powerful your model is, whether it's statistical model or machine learning type of model. Most of the work in these type of projects goes into data preparation. You go through and do data cleaning. It's a lengthy process. And at the end of it, applying the analysis is usually fast. Unless you have really, really large data and you don't have computing resources to calculate it, it's fast. That part doesn't take long, but preparing your data to get there is the longest. And then you do the analysis, you look at the result, you find out something wrong that's related to bad data, you have to go back and fix that and then rerun it again. Overfitting problem we talked about. You may be fitting your model perfectly for your training data, but must work for the validation data. This is a pitfall that a lot of people fall into. To avoid this, you have to really have a truly independent validation data set that is truly independent from your training data set. I have a typo there. Testing. No, not the typo. So the validation data set has to be truly independent from the training. And what most people started doing nowadays is that they blind the people who are developing the model from the validation data set. So they don't even have access to it until their model is complete and it's ready for validation purposes. So that helps. Otherwise, people put in all kinds of biases into their modeling. Another challenge is that you don't have a clear guidelines in terms of which method would work best for a given project. In statistical analysis, on the right-hand side, you see there are decision trees like, okay, is your data nominal? Then you go this, or it asks you questions in terms of what your problem is, and then it guides you to the right statistical tool. We don't have much of that in machine learning methods. We have some in terms of classification as supervised versus unsupervised, etc., but not much. So what people usually do is they use many classifiers, many models for a given problem, and these are not repeatable. So it's not like you have one model, it's going to work on your next project as well. You have to develop another one. And then for each project you develop multiple, and then you evaluate their performances. And there are some things called receiver operating characteristic graphs to be used for the area under the curve on those graphs are used as measures for best performing models, and these are measures of sensitivity, specificity, not too complicated. And to conclude, some of the, and again from this article, they are suggesting that some of the disruptions and benefits that are going to be seen in the discipline of medicine are we're going to start getting more accurate prognoses by utilizing machine learning because we're not only looking at pieces of data now, we're able to use the entire data set about that patient, whether it's their precision medicine type of data, microbiome, genomics, or data, their structured and unstructured data in their EHR, genomics, of course, and the data that's coming from their variables, Internet of Things type of thing, all that data, their claim data, etc. The data about the population that they live in, depending on their geographical location, all that data is coming together. So that's going to give us more accurate prognosis, more accurate diagnoses. And in terms of disruptions, they're thinking that it's going to probably replace some radiologists or anatomical pathologists because machines will start reading those images better than them. I have these three references that might be useful, and that's about it. Any questions or comments here or online?
We have a few more people join, I think, online.
Yes, we have
How many do you have?
12 right now.
Good.
Yes. Any questions from online attendees?
What type of expert systems or AI are being run in the background now?
In medicine, there aren't any that I'm aware of that are mainstream that are truly based on clinical data. There are many that are based on peripheral data like social media data, the variables data, Internet of Things. And there are lots of research projects that have been completed that are serving an individual organization for a particular thing. One thing that's been amazing was there was this project where they are able to get people with paralysis, they were able to get signals from their brain and interpret that with machine learning and send the results of their interpretation to their muscles and be able to grab a cup, drink, do some simple movements, even though they're paralyzed. Those kind of projects have been around, and they're doing it well. But there isn't a mainstream product that's being used that I'm aware of.
Or solve some clinic, the same clinic question, for example, we want to find the best way to diagnose some diseases. So different, for some different papers maybe give different answers or some different models, no matter from the regression models or from the many machines, because they can contain different covariants or the factors in it. So how can we differentiate the good or bad or the quality of these papers? That's the first question. The second question, can we combine the results of these papers together? Because like metastasis, we can combine all the factors or results, outcomes together to get new models for the results.
Can you repeat the question or summarize it so that the online...
Because I understand the question was, one is there are lots of papers that are using different models, sometimes even on the same problem. How do we actually evaluate which one is better? And when we look at different papers that are published, of course, these very under the curve type of evaluation methods are what's utilized to give a measure of how successful the model was. That doesn't mean that there aren't biases going into or changing your model to actually overfit just for that project. Those kind of things are hard to detect in the literature. So given that, of course, people use different data sets even for the same problem and then come up with different results. It's very hard to gauge. I think one way to go there is there are efforts in terms of reproducibility, and nowadays journals are asking people to submit their own data sets and sometimes their own code that they've used as part of their publication. So as this increases, then same study with the same data set, with the same methods will be able to be reproduced in the more it's done on a particular concept, we will be able to know the better what the outcomes are. So I think that's the only way going forward. Otherwise, people are working in silos, and these are not comparable. These are apples or oranges. So even if it's the same project, the data sets are different. So and the methods are different. It's very hard to compare. Could you repeat the second part of the question?
The second part is that what you have answered is how to combine all the data. Like the meta-analysis, we can combine some analysis qualities or the quantities of the research to get which is best or which is bad, and we can combine the data or cohort of the data together to get the better results or to test the models whether they're better.
Yeah, there are lots of effort going on in terms of data commons at NIH. I think there's an NSF also supporting this, ARC is supporting it. There are lots of funding going into creation of data commons. These are not necessarily data commons for the research data that's being utilized, but that's one aspect of it. So data commons for research, which would include the data and methods that are utilized for a given publication. If that exists, then I'm imagining a system where you would be able to go and look at a paper and click the data set and hopefully have their methods clear enough to be able to repeat it in a relatively short amount of time. And then that would increase the confidence on those results.
But the question was, could you combine things from different, could you make one big model? Was that part of your question?
Yeah.
Can you combine from
one big model or one?
If you read 3 papers and they each use a different model around the same problem, could you somehow develop a model that combines all 3?
I see. The question is, if you read 3 papers on the same topic that have that use different models, can you just combine them to come up with a better model? Not sequentially or parallel in a easy plug and play type of way. However, you have to, like one of the problems that we talked about, one of the challenges that we talked about, it requires semantic understanding of what's going on in those models for each of those models. If you are able to study each one in such an extent to be able to understand what really went on within those models, then you would gain insight to be able to come up with a new model, not necessarily a combination of those 3, but a brand new model that's better than those 3. So no easy combination of models.
Any questions from the online people?
Any questions from the online attendants? Check the chat window. No?
Okay, because I want to tell everybody about next week.
Okay.
And then, well, first we should thank Dr. Ozaydin. But I want to tell both the online,
I'll just
I was going to say, yeah, for next week, and actually I'll probably get to it shortly after today. The next live session is not until July 12th. And then we'll have GoToMeeting and live like we're doing today. But in between that, I'm going to provide you with materials that are online. And I will send them to you directly with you. I'll send you the instructions with your email. I mean, so that's why I want to remind the people online, we need your email. If you did not sign in with your email so that we have it, just send it to me separately. It's eberner, E-B-E-R-N-E-R @uab.edu. Because I'll send out the materials from today. I've got the references. There are many more than 3 references, but the 3 that Dr. Ozaydin cited, we're actually going to give you links to so that you can get them. But anyway, so as we did the first time, hopefully all of you got the materials from the first time. I will be sending out copies of the slides, the link when we get it. It'll take a little while to get this online, but we'll get it online. I'll send you the link. And what else do I send? And the readings. Send that out, but I also at the same time will send you the materials for over the next couple of weeks on, and the topic for that is, I think, I forget the title of it, but it's on EHR data and EHRs and using EHR data for research. There'll also be an exercise for you to actually try I2B2 that we've mentioned with it, and then we'll discuss it on July 12th when we meet again. Any questions about the process? That's why if some of you are coming in and out of the sessions, I just need to know if, let's say you didn't make one of these sessions, but you wanted the materials, just let me know and I'll send them. But I won't routinely send them to just everybody. Are there any other questions here or online? Not?
A question. Still, still question. How, I mean, there's a lot of research about the models you use machine learning to a lot about clinical research, I mean. But how, as you know, how many of them have been truly used in the, applied in the clinic to solve the clinic problems? I mean, because different people have different results or as models, are they actually be used in the clinic to solve the problems?
Especially the machine learning models, they need verification. Just like a new drug goes through clinical trials, gets verified over and over again in multiple levels. It doesn't go into clinical practice, and these are the same. Did any of them get into practice? I don't recall off the top of my head, but I can check. I can check and let you know.
Well, the references in your chapter are examples of where they've been done. I mean, but it is research, you're right.
As research,
primarily research.
But as a mainstream clinical practice, I don't recall any off the top of my head right now.
So what's the relationship, as you know, in clinic, what's the relationship with of the guideline with and the result of the machine learning? So when the clinic want to solve a problem, no matter the diagnosis or want to give the prescription, which can machine learning results or the guideline can give the best results or reference to the clinicians.
I think, I was going to say, I think it depends, because the guidelines, remember, come from evidence-based guidelines, come from, you know what I mean?
Yeah, I think
Evidence, the question was, which works better in a clinical setting, clinical guidelines or machine learning? I think, as Dr. Ozaydin said, machine learning is still very new and not entirely fully accepted yet.
Yeah.
But the point is, evidence-based guidelines are based on evidence. And I think it's very likely, and I think you said it still needs further verification. So if the machine learning algorithms give you sort of guidance, let's say the model provides some guidance for clinical care, after it undergoes more testing, it may very well find its way into guidelines, so that the guidelines may come from evidence from a variety of sorts.
may include machine learning.
And may include machine learning.
I read that there's evidence that in radiology, machine learning algorithms outperformed radiology.
Well, that's right.
Yeah. So there's that example. There's also a collaboration between Watson and MD Anderson, that kind of fell apart though. It was promising to an extent. I think earlier this year it kind of fell apart. They separated their ways. Watson is going to partner with someone else and continue their projects. That was directly, I think, that they were trying to make it part of their EHR system, have the Watson type of decision support systems directly part of their EHR. But currently did not materialize.
The radiology one is a good example, and I know that they suggest radiological diagnoses or point out areas of radiological of the films that are abnormal, and that is pattern recognition approaches. But usually they are still being used in conjunction with a clinician who has to decide if they're right or not.
Yeah, one of the reference articles talks about in detail about the liability issues, the issues that are related with policy, especially on the radiology, so that those are not technical problems, but real problems that are in front of us before any of this goes into mainstream.
Well, thank you.
Thank you.
Guess you can't hear the online. Yes. And I'll be back in touch with you about next materials over the next few weeks.
Okay.